left with dx. And looking at this, what I can do that for each of the three directions, so do it for the y and the z direction as well, and then sub that into equation 1. So the energy equation. And when we do that and I rearrange a couple of terms a little bit, we get the following. Okay, so that is our equation. We're getting places with this now. And first of all, we notice dx, dy, dz is on both sides, and so that is going to cancel out. Oops, I got a little error there. I'm sorry. That should not be dx. That should be dt, because we're looking at the energy storage term. And so that's representing the energy that could be increasing or decreasing in our little differential element. So this equation now becomes the basis for our energy diffusion, heat diffusion equation, I should say. And there are a couple of other simplifications that we sometimes make. And first of all, if the thermal conductivity is a constant in the object, we'll notice that it's there, there, and there. If thermal conductivity is a constant, we can pull it out of the partial derivative operator for each of those terms. So let's do that. So that is if thermal conductivity does not vary around the object. If it's a constant, we can pull that out. And then I'm going to divide by the other terms. But what we end up with is the following. And these terms I'm dividing by the thermal conductivity because we pulled it out of the first three terms. And then the energy storage is this term. Okay, so this is becoming our heat diffusion equation. And let's look at each of these term by term. And so what we have here could be a representation. Essentially, it's conduction or diffusion. And this mathematically can sometimes be represented as being del dot grad of T. And mathematically, that is also written as del squared T. That is a Laplacian operator. And so that is the first three terms that we've clustered together. The next thing we have here is our Q dot term, and if you recall back, that was the generation term. So that is generation of energy, and where are we going to generate energy in a solid? Well, there are different ways you can do this. You might have nuclear decay, and that is then generating energy. You could have chemical reactions. And if it is exothermic, it'll be generating energy. Endothermic, it'll be absorbing energy. But no matter what, you're going to have a change. Electrical resistance, we have the heating effect within electrical resistors. And that can also generate energy. And so there are other forms that you can generate energy. So those are examples of energy generation. And then finally, on the right-hand side, this is our storage term. So energy storage. So that is the heat diffusion equation in its most non-simplified form, so in its most general form. Now what we often do is we simplify this a bit, so I'm going to look at a number of different ways of simplifying the heat diffusion equation. First of all, let's assume that we have steady state. So if we have steady state, what that implies is any term that is a derivative with respect to time is going to be 0. So looking back at the heat diffusion equation, the only place where we have a derivative with respect to time is our storage term over on the right-hand side. And so that term would disappear. So that would be if we have steady state. Another simplification we could have is if we had a transient, so the time derivative remains, but no heat generation. And so that would be Q dot equals 0. And another simplification that we can have is we can have steady state and no heat generation. And that would imply the derivative with respect to time is 0 and q dot is equal to 0. And with that, then we are just left with the Laplacian and that would be equal to 0. So that is the heat diffusion equation. Now, as with any kind of equation, differential equation, be it ordinary or partial differential equation, we need boundary conditions in order to solve this. So we need boundary conditions to solve for temperature x, y, z, or t. So boundary conditions are what are required. We take this equation, the mathematical physics equation, coupled with the boundary conditions, and then we can determine what's going on in the inside. And how you do that, that's another matter. It could either be numerically or you do it analytically for very, very simple types of problems. But anyways, what we'll do in the next segment, we're going to take a look at the boundary conditions that apply to the heat diffusion equation. But that is the heat diffusion equation, and you can use this to determine the temperature distribution within an object